Assalamualaikum, my name is Mohammed Shumas. You are watching my YouTube channel. In this video, we will see that how we can simulate methanol in Aspen Plus. So let's start. First of all, I am having a case study and we will move through our case study. So we are having a case study in which have been given the flow rate. 1500 kg mole of flow rate is present. The composition of this flow rate is consisting of hydrogen, carbon monoxide, carbon dioxide and methane. We have to convert these components that are present in reactants with these reactions into methanol in a CSTR in this CSTR. So the temperature, operating temperature and pressure of CSTR have been given to us, and the volume. We will also use this volume while simulating our CSTR. For simulating CSTR, we need to have equilibrium constants for these two reactions. So these equilibrium constants have also been provided to us. So now this is a short introduction. After the feed will enter in the reactor, we will be having two type of things. You can say that we will be having our reactants and products. For separating our reactants and products, the reactions that are unconverted, we will use a separating drum. We will have to find the best temperature at which maximum amount of methanol will be part of the bottom product with water, and the unreacted gases will leave from the top. So we want the best temperature at which a very minimal amount, you can say only 1%, go through the uncondensable, or you can say unconverted gases, that are H2, CO2 and methane. After this vapor stream, we will recycle them because we cannot waste our unconverted reactants. So we will recycle them. So the bottom product that will be produced from this separating drum will be having methanol and water, and we will use a distillation. First of all, we will use a shortcut, and then a red frac column for rigorous calculation for the separation of methanol and water. So I have made a small flow diagram of this case study. So you can see that this is our feed, its temperature, pressure, the composition. So to make our feed temperature and pressure that is required in a CSTR, we will use a compressor and a heater. And for as in the case study, it was that our reactor is operating at 80 bar, and this separating drum we have to operate at 20 bars. So this is the valve that will reduce the pressure, cooler will reduce the temperature, and we will achieve flashing in our separating drum. Methanol and water will go to this side, and unreacted gases will be recycled. So we are again having a valve to reduce the pressure, because our distillation, we have to perform distillation at 1.3 bar. So again, a valve is present that will reduce the pressure from 20 bar to 1.3 bar, and here we will use a distillation column to separate out our methanol and water. First of all, we will do with shortcut method, and then we will proceed to rigorous method. So let's move to our simulation, and when we will simulate, there will be a little bit differences in this simulation. So let's move to our simulation. So first of all, I will add my components. So my components are hydrogen plus second component is CO. My third component is CO2 and CH4, and my fourth component is the product, that is methanol. So it is methanol. After that, our last component is also our product, that is water. So now after this, I will press this next button. Here in the property methods, you can go with Penn Robinson. So it is Penn Robinson. I will press this next and just press this run button. Now you can see that results are available. I will directly go to the simulation environment. Here, first of all, if you see our flow diagram, I have to define a compressor and a heater. So I will specify a material stream, and I will go to pressure changers, and I will select a compressor, and then I will go to my exchangers, and I will select a heater. So now I will press this material stream and connect this material stream with this one, and this material stream the will be the our heater outlet stream. So I will double click on this arrow and join it with our compressor. Quickly I will name them as I will specify my streams, that is feed stream, and that is, you can say, my two is compressed uh, feed stream, and this is our you can say heated stream. So okay, you can name any of the names you can want. So this is our B1 block, and this is our this is B2. You can rename as HX, and for this compressor you can name as compressor. So now I will double click on that this feed stream to specify my feed streams. So now temperature. What was the temperature of our feed stream? The temperature of our feed stream was where is the flow rate is 1500 kg per hour at 100 degree and 20 bar pressure. So temperature is 100 C, and the pressure is 20 bar. The flow rate is 1500 kg per hour. Here we have been given as mole fraction, so you will give mole fractions, and you can give the mole fractions for hydrogen. The mole fraction was 0.60. For CO it was 0.18. For CO2 it is 0.20, and for methane it is 0.02. So I will drag it down, and here you can see the total is 1, so it is good to go. After this I will press this next button. So now in compressor, we are simulating a compressor. You have to select a type. So you can, in this case study, we haven't specified any, so you can go with isentropic using ASME method. You have to define one of these things for the simulation to happen. So here we are being given with the discharge pressure, that was the pressure of our reactor conditions, that was 80 bar. So I will give as 80 bar as my pressure. You have to give the isentropic efficiency. So in the question in the case study, that two haven't been identified, so you can write any. So you can, I am giving just random values. So if you have been given with these efficiencies, you can write them as well. So it is a green blue tick over here. So we are good to go. We have inputted all the required parameters that are required for our simulation. So I will press this next button. So now it is the heater. So we need here two type of specifications for the input to be completed for the simulation to happen. So here temperature, we have been given that the reactor inlet temperature is 280 degree. So I will write here as 280 degree. Pressure, we have already at the compressor discharge we have given at 80 bar. So I will write as 0. So you can see that our run button has been activated. I will press this run button, and so you can see that our results are available. So I will go to the main flow sheet, and you can say that our simulation has been converged, or you can say performed till now. After that, the next step, if we go to our flow diagram, we have to install the CSTR. So I will go to the reactors, and here you can see that it is a CSTR. So I will pick and drop it over here. It is our CSTR. It is for by default P3. So I will rename as reactor. After that I have to specify a outlet stream. So I will press this material and I will specify my outlet stream. I will press this double click and connect my compressed heat, compressed and heated feed with this reactor. So I can rename it as reactor out, reactor out, reactor out. So it is our reactor out. So I will double click on the reactor for defining my reactor. So here we have to, in specifications, we have to define minimum of two parameters in the operating conditions. So operating pressure is 80 bar. The temperature was 280 degree C. So I had specified my two things. So the our reaction will only be in vapor phase. So it is vapor phase. We have to define the reactor volume. So here, what was the reactor volume? It was 7.3 meter cube. You can write in meter cube, or as well as liter. In liters it will be 7500. So if you write in 7.5, so you have to select what is cubic meter. So it is 7.5 cubic meter. Now you can see that our specifications input has been completed. So now I will go to the kinetics. In kinetics, you have to define a reaction set. The reaction set will consist of these two reactions. These two reactions will consist in our reaction set. So I will select new reaction set R1, and it is a its type is it is not ionic, it is journal. So journal. Okay. So now you will drag it down and see that in reactions, your reaction set has been appeared. So I will, for defining my reactions, I will press this new, and here again it is a journal. So you will have just close it. You will double click on it, and now this reaction set has been opened. So you will select this new, uh, name it as it reaction 1. It is not a power law. We are have been given with equilibrium type of reaction. So you can say that it is the equilibrium constant of this reaction. So it is a equilibrium type of reaction. So will be equilibrium. Our components for the first reaction are CO plus H2, and in our product we are obtaining methanol. So here in the coefficients for reactants, you have to apply a negative sign for the indication that they are reactants. So the stoichiometric coefficients that are present, you have to apply a negative sign with them. So in products, you will go with a positive integer. So I have defined my reaction. So I can just close it. So here I will now, because we were having two reactions, so I will now define my second reaction. It is also a equilibrium type of reaction. You can name as it reaction 2. So now again the second reaction was CO2 was reacting with again hydrogen to produce methanol and water. So now I will again specify my, you can say that stoichiometric coefficients. For stoichiometric coefficients for reactants, I will apply a negative sign. So it is -1, it is -3, uh, and in products, was having 1 mole of methanol with 1 mole of water is produced. So now it also says the next, so it is okay. So now we are good to go. So now you can see that the run button has been activated. So I will press this run button, and you can see that results are available. So now I will go to my main flow sheet, and here you can see that my results are available. I will double click on it to see my results. So if I go to my reactor. Where is my reactor? This is my reactor. So if I open my reactor and here stream results, if I open my stream results and I go to the mole flows or mole fraction, so here you can see that in methanol, in reactor out, a very small amount of methanol is being produced. So ideally you can see that no reaction is happening because we haven't give the equilibrium constants in the simulation till now. So I will again go to my reactor. I will go to my reactor block. Just wait for a minute. I will double click on it. Go to the kinetics. In kinetics, sorry, I have to go to my reactions. So these are reactions, and this is called equilibrium. So after pressing the equilibrium, what was now it is calculating the equilibrium constant from Gibbs energies. So a very small amount of you can say that conversion is present. So I have changed my reaction phase to vapor phase, and I will compute the K from built-in expressions. As it is a gaseous phase reaction, so you can for equilibrium constant you can write as fugacity, and for A you have to go to these components and you will write here these values, sorry, you will write in the equilibrium constant. So I am writing these values. The first value is minus 12.34, and for B it is 5670. So it is okay. So now I will go toward the second reaction. It is also a vapor phase reaction. I am asking Aspen to commute the expression from the equation that I am giving. Again, I will press here as fugacity. For A, I am having 12.15. In B, the value is 4500. So now again you can see that run button is activated. So I will press this run button and wait for my results, and you can see the results are available. I will go to the main flow sheet, again double click on it, and go towards my stream results. And here now I will again go to the mole flows, and here you can see that now a large amount of 389.893 you can say what are its let me kg mole, what are the units, so it is kg mole. So 389.983 kg mole of you can say that methanol is produced. All the hydrogen is consumed. CO is almost all the CO is consumed. Methane was present as such because it is not taking part in the reaction. CO2 is present, but CO2 is still present. But you can see that CO2 is reacting with hydrogen for the production of methanol. So if hydrogen is all the hydrogen is consumed, so CO2 is now leaving as unreacted here in the CSTR effluent. So now water is also produced. So now these results are acceptable. So now what our next task, we have to separate out the reactants and the products. For this I have to reduce the pressure and cool our reactor effluent for effective separation or flash separation to happen. So I will go to the pressure changes. I will select a valve, apply here, and then I will go to the exchangers, and here I will select the heater, or you can say a cooler. I will in Aspen Plus you can there is only one block for heater cooler. The outlet temperature defines its function, that it will act as a heater or a cooler. So I will click on this valve to increase its size, otherwise it will disturb me in my connections. So this is my, I will double click on it and say it is valve, and I will double click on it and say it is a cooler. So now I will drag it. Now I have to specify material stream. So I will select this material stream, and I have to select another material stream that is from this one. I will press this arrow, double click on it, and join it with this one. Double click on it and join it with this one. So now this is our, this 6 is our cooled cooled to sep. So I cannot not write. So you can only say to separator. It is our cold feed going to the separator. So just making a few cosmetic changes. Now I will double click on this valve, and I will define the outlet pressure as 20 bar. All the, you can see that all the inputs are completed. So now I will press this next button. Here again, for in the previous heater, I had said, I had told you that we have to define two things. So pressure drop, I again will say a 0, so it says that no pressure drop. In the accelerator, it is an ideal case, but for it we can take it. So now the temperature, if you go to the simulation, we have to find the best temperature. So for the best temperature, we will use a thing that is present in Aspen Plus, that is design spec. For the start, we will give an initial guess that say that we give 60 degree. We have to give an initial value, and then we will use the design spec to minimize the methanol that is being produced in the recycle, or you can say the top product of our separator. So now one thing I had forgotten, I haven't applied till now a separating drum over here. I will go to the separators. This is a flash 2. I will select, I have pasted over here. I will go to the material streams. The top product, the top is defining the unconverted reactants, and this bottom will be consisting of our methanol and water. So I will double click on this and connect it with this. Now I will double click on it, and here the temperature, the operating temperature, I will give the same as in the cooler, because we have to find the best temperature. And the pressure drop, you can write as 0. So another good thing, while you are simulating a separating drum without defining temperature, it is good to define the duty, because sometimes if you define the temperature, the energy balance calculations uh, did not converge in Aspen Plus. So I had given the duty as it is adiabatically the separation will happen. Pressure, I will say it is 0. It 0 says that 0 pressure drop happens in the you can say 0 pressure drop is happening in our separating drum. So I will press this run button, so you can see that our results are available. So P6 is our separating drum. I will double click on it to make it separator. So it is our separator. I will double click on it, and again you can press this run button. So now what was the top product? It is 7. I will say, rewriting the top, and the okay, top is reserved, so you can write as TP. So I write TP, and you can write as bottom, BD for our bottom. So now I will double click on it to see my results. Again, press this run button. Separator stream results. So I will go to the stream results, and here in the molar flows, you can see that in our bottom, out of 389 at this 60-degree temperature, 382 is going to the bottom and 7.84 is going to the top product. And out of water, the maximum water, that is 120 kg a large amount of water is present in our bottom product. But we are concerned with our main product, that is methanol. So we want this 7.8 to be less, you can say 1 or 2 kmol only. If you go to the mole fractions, so the mole fraction is the mole fraction of methanol in our top product is 0.04. So just to it is also a very good, you can see that it is good separation, but I say that I don't want, I want that it is to be zero less than 0.01%. Now I will, for what value of this 0.01% to be in our top product, what will be the temperature. So we will find this by a very powerful tool that is present in Aspen Plus, that is Design Spec. So just go to these manipulators. Here you will see that this is Design Spec, and paste it over here, and you will just now double click on it. So first of all, you will define a variable. So I will write as optimize meth. I had, after this, you will, so it is the variable. So go to the type of, so what is it, is a mole fraction. It is mole fraction of methanol that we want to be less than 0.01%. So in what stream? In stream top product. Component is methanol. So now all things are completed. We will go to the spec. Here we have to again write our variable. So second click on it, variable list, and just drag this variable list to here. So now what is the target value? Our target value is to make it 0.01. And with how much tolerance, you can say that tolerance, you can write 0.001. This tolerance value define that how much tolerance or plus minus you can accept in this target value. So after this, your spec value also has also been defined. So now what thing we we want to vary for getting our this spec, that is 0. Less than, or you can say 0.01 mole fraction of methanol in the top product that is leaving the separating drum. So we will manipulate the temperature of the cooler. So it is a block variable. So it is block variable. It is what was the block? It was cooler. And what thing we will vary, that is the temperature. Here you have to give the lower and upper limits. So I will giving a lower limit as 0, the upper limit as 100. So now you can see that run button has been activated. I will press this run button, and you can see that results are available. So this is our design spec. You will go to the results, and here you can see that 27.81 is the temperature at which you can see that the value has been changed from 0.04 to less than 0.01%, that is 0.009%. It is with the tolerance value of 0.001% that I have defined. So it is a good thing in Aspen Plus that it has already, the results are already been defined with our this value, with this value. So if you double click on it and see the results, so now you can see that it has already changed the results with on the design spec temperature. So now again go to the mole fractions, and here you can see that the mole fraction of methanol is 0.009%, and the mole, if you see the mole flow from, so from 0 388 point 385 point, so it was roughly here, roughly 7.8 kg moles were present. So now it has been reduced to 1.65 kg moles. So now this was the design spec. After this, we have to recycle. We have to recycle the stream. So for recycling this stream, I have to apply a mixer over here. So I will go to mixers, and here I will, so I can add a mixer over here as well. So insert, go to the insert block, press this yes, reconcile, and press this OK. So now here you can say that it is a mixer and press OK. So now say that no pressure drop, just press this run button, and go to the main flow sheet, and here it is a mixer. Just drag it over here. So now, now I will just press this top product and supply it over here. So now see it converges or not. So now I will press this run button, and it says the results are available with errors. So let's see that what are our errors. So the convergence in separation is not happening because due to our mass flow differences. So whenever you simulate a recycle stream of unconverted reactants in Aspen Plus, it is necessary to purge out the stream for the mass balance calculations to, you can say, converge. So here I will insert a block, yes, and yes, and now I will insert a feed splitter that will act as a, you can say that it will act as a purge stream. I will purge some of the unconverted reactants and see that it converges or not. So it is, I will drag it over here. I will rotate it to make it little look some good. So it is material stream. I will select as uh, this one. So now I will now double click on it and specify that 0.7%. So initial gas 0.7% of the stream, the flow rate is purged. So now again I will press this reset as error was present, and now I will press this run button. So now you can see that results are available. You can optimize this value. You can write 0.6, 0.5, 0.8, any value that you want. You can optimize it, but I am not going in the more details because video will get more lengthy. Now you can see that our stream has been converged. So now after that, what was the next thing? The next thing was we had installed a separator. We have find the best temperature, and the liquid stream contain above 95% of methanol, and we have above 95% of methanol and water present in vapor stream, and we have already done this as because in methanol, the thing that is leaving, that was less than 0.01% of methanol was leaving the top product. So now we had also recycled the hydrogen, CO, CO2, and other gases back to our system. So one last thing is we are, and we have been left with one last thing, that is design a distillation column. So let's move towards the distillation column. So we will again use so I will make a cosmetic changes. So now in the, So now after this bottom, we will again use a pressure changer, that is a valve. We will use it over here. So it is a pressure valve. Double click on this. I will make it a bit bigger. So now where was the valve? Where was the valve? Here is this valve. I will double click on it and connect it with connect the bottom with this valve. This valve will let down the pressure. You can rename it as it is valve 2. After this, I will specify a material stream outlet that will be having pressure that is 1.3 bar. So after that, I will first of all in the problem it had said that you will do this by shortcut distillation. So I will select this shortcut distillation method over here and press this. I will okay. Now I will again press the material stream. This is our distillate, and here we will be having methanol, and this is our water. Press this. Uh, so now here we will be having methanol, meth, and 12 I rename as water. So after this, you can name 10 as feed to distillation. Okay, just drag it over here. Double click on that and make its connection with this. So now I can rename this B10 as distillation. So now that is okay. So now I will double click on it, and here we haven't been given the number of stages, so I will give an imaginary number as 10. Or you can see if in the reaction it has given that reflux rate is given to us. So don't give this number of rates, we will give the flux ratio, that is 1.6. So in Aspen Plus, here it is written as key component recoveries. So here in Aspen Plus, the light key in heavy key only defines of the top product. We have to define the specification there of only the top product. So light key in the top product and the heavy key in the top product. So what is the light key in the top product is methanol, and we want its separation to be 0.99% of its separation. What is the heavy key in the top product? It is water, and we want water to be less than 0.0 or equivalent to 0.01% in our top product. So condenser, the operating pressure is 1.3. So you can write here a small value, then 1.3 it is 1.2. The boiler you can write as 1.4. So I will write as 1.4 for my boiler pressure. So total condenser. So my all the things have been defined, but it says that next button. So I will press this next button. So I haven't defined my outlet pressure in my valve 2. So I will define that my outlet pressure is 0.1, oh sorry, 1.3 bar, and that is present over here, 1.3 bar. So now you can see that run button has been activated. I will press this run button, and it says that results are available with error. So now what are the results? So it says that, oh, temperature down to the lower limit 89 point. So what has happened? Because in our simulation, sorry, in our simulation, if you see in our this feed stream, a small amount of carbon dioxide, hydrogen, and methane were also present. So that is affecting the vapor liquid equilibrium of methanol and water. So it is the Plus is not going to calculate this. So now what we will do, we will again we have to again insert unit block. So we will insert a block that is component separator. So we go to the separators. Here is the separator. So double click on this, insert block, say this yes, yes, and here you will feed splitter. So you will press this all types and then go to that, and here you have to find a separator. You have to find separator. So this is sep. So this is a separator. So now I had installed a separator. This separator will separate out all the unconverted gases that are accompanying with methanol and water from the stream, and then we will again simulate our distillation column. So for simulating, I have to define another stream. So I will define another stream. Oh, it has wrong. So it is wrong. So I have to define another stream. So I will press. Uh, so now this is my stream. So I will press this. So now this 14 stream will consist of all the unconverted small amount of hydrogen, carbon dioxide, and carbon monoxide and methane that are accompanying water and methanol. So I will write here as 1, 1, 1. I will rename as 14. So for 14, 1, 1. So it is saying that I have defined here at 1, so I will remove them. Or you can general for this stream you can say that it is having methanol and water only. So all the other things will go to this 14 stream automatically. So press this run button, and now you can see that after that my distillation column has also been converged. So that was the error, and we had seen that how we can remove this error in our Aspen Plus. So now this is our shortcut distillation method, but in the question it has said that perform these calculations with rigorous distillation methods as well. So I will double click on it first of all and see that what are the results of these. So what are the results? So results, so go to the molar flows. So you can see that in our methanol, a large, almost all the methanol is going to our top product, and almost all the water is being separated from our bottom product. If I go to the mole fractions, so the mole fractions are also approximately satisfying. So 0.09% of methanol is in the top product, and 0.01% that is very near to 0.0, it is 0.03, that is very near to 0.01% that was being asked in our as our input value. So just go to the summary, or you can go to the results, and you have to while simulating the rigorous column, you will need all these calculated values. So I will just so if I can increase, okay, so I will take a screenshot of all these values, sniping with snapping tool, so that I can use these values. New. So this is my sniping tool. Just save it. From where it will save, yeah. So save. This is save. I will save it onto my desktop, and okay. So I will minimize it. So I will again go to my mail flow sheet. I will press this select this distillation column and press delete. So now I will go again to the columns, and here I will select my, so now I will again make it a little bit bigger so that values are values of so now I have made a little bit bigger because my module palette names were not appearing. So now this is the regress distillation column. I will press and place it over here. After this, I will just double click on this stream and connect it with this. I will press this and connect it with this one, and press this water and connect it this with this one. So I can increase a little bit of its size. So now this is our rigorous distillation column. So again, you can rename it is at distillation column. Name I had given wrong, but it's okay. Let's go. So what are the number of stages you have? So again, go to that value and see that what are the number of stages. So the minimum number of actual number of stages were 9.07. So you can write as 9 is the number of stages. Condenser was total. So total. V-boiler is kettle type. Valid phase is all okay. So now you have to define minimum of two specifications here. So what is the distillate rate? So you can see that what is the distillate rate. Distillate rate is not given to us over here. So it was given in the molar flows. So you need not to worry. We can find the actual reflux ratio. Actual reflux ratio is 1.6. And other things that have been given to us is the feed. Uh, you can write distillate temperature, bottom temperature, reboiler duty. So you can also reboiler duty 267,999 and 0. So it is our reboiler duty for streams. Feeds. What was the feed stage? Feed stage was above 9, so it is above stage, and you can rewrite as above 7. So it is all okay. For pressure, you have to define the condenser pressure. You can, as the operating pressure of the column was 1.3, you can rename as condenser pressure as 1.2. So now all the inputs have been completed. You can see the run button has been activated. You can press this run button and see that results are available. So now results are available. Go to the stream results, and here you can see that in our mole flows, you can see that uh, 3 out of 388.408, 383 kg mole is present in our bottom product, and water is with water is 4.48. So the mole fractions are this. If so, that's all for this video. I hope you like the video. In this video we have seen that how you can simulate a methanol production simulation in Aspen Plus. I will also perform the same simulation in Aspen Hysis. I hope you like the video. Inshallah meet you in another video. Allah Hafiz and Assalamu alaikum.